Hey everyone, welcome back to my another tutorial about YOLO v4 custom object detection with TensorFlow. So to be state-of-the-art model, YOLO v4 needs to be the leading edge of deep learning. So YOLO v4 authors have worked on techniques to improve the accuracy of the model while training and in post-processing. There was a lot of techniques that are called bag of freebies and bag of specials. In my previous tutorial, we mostly covered the YOLO v4 backbone, the neck, and part of bags of specials for the detector. So in this part, we will continue with bag of specials and we'll cover bag of freebies. So here is the complete list from YOLO v4 paper, and here is bag of specials for backbone, for detector, and bag of freebies for backbone and detector. And this is actually everything what I'll try to cover in this tutorial series shortly. At first we'll cover the theory, and at the end I'll shortly show you how you can test my YOLO v4 implementation and how you can train your custom model. So I will begin with a bag of specials for backbone. And if you would look at YOLO v4 backbone, you might see that it uses a mesh activation function in the backbone. So mesh is another activation function with a close similarity to ReLU. As claimed by the paper, mesh can outperform a lot of activation functions in deep networks across different datasets. As you can see from this table, there is a lot of activation functions and their results, mean accuracy, mean loss, standard deviation, and so on. And as we can see, the ReLU takes the 4th place and the mesh activation takes the 1st place. So this was used in YOLO v4, and of course we can use this in any deep learning model we develop. So mesh is a novel, smooth, and non-monotonic neural activation function which can be defined as follows in this slide. And as you can see, its function looks a little bit different from ReLU, and of course if you are looking at this tutorial, you should already know how ReLU looks. And I'm not going to explain this here. This activation function shows very promising results. For example, using a squeeze-excite network with mesh on CIFAR 100 dataset, it resulted in an increase in top 1 test accuracy by 1.5 and 1.76 as compared to the same network with Swish and ReLU respectively. I don't have slide to show this, but that's only an addition. Next, I would like to talk about multi-input weighted residual connections. And in recent years, researchers have paid a lot of attention to feature maps and what will be fed into convolutional neural network layers. Almost all recent object detection models start to break away from the tradition that only the previous layer is used for the next layer. So, how layers are connected in object detection becomes more and more important now. I already mentioned that in my previous tutorial while talking about FPN and PAN. Now I'm showing you another diagram that shows another NAC design called BFPN that has better accuracy and efficiency trade-offs according to its paper. In YOLO v4 paper, authors compare its performance with the EfficientDet, which is considered as one of the state-of-the-art technology by YOLO v4. As shown in this slide, EfficientDet uses the EfficientNet as the backbone feature extractor from this slide as the NAC. And as a reference, the following diagram is the architecture for the EfficientNet, which builds on the MBCon layer that compare on the inverted residual block. So the key advantage of this is that it requires much lower computational resources than traditional convolutional layer. In many machine learning and deep learning problems, we learn low dimensional representation of the input. We extract the core information of the data by creating an information bottleneck. That forces us to discover the most important information, which is the core principle of learning. Following this principle, an inverted residual block takes a low-dimensional representation as input and manipulate it with convolution and non-linear operations. But there is a major issue on the non-linear parts like ReLU. Non-linear operations stretch or compress regions proportionally. So in such comparison, inputs might map to the same region points. For example, ReLU might collapse the channel in low-dimensional space and inevitably lose information. To address that, we can temporarily expand the dimension, the number of channels with the hope that we have a lot of channels now and information might still be preserved in some channels after the non-linear operations. Here is the detail of an inverted residual block in this image. So here actually is a bottleneck residual block transforming from key to k channels with stride S and expansion factor T. As shown here, the low-dimensional representation is first expanded to T key channels. Then it is filtered with a lightweight 3x3 depthwise convolution. And then features are then subsequently reduced back to low-dimensional at the end of module. So here is another slide where non-linear operations are added when it remains in the higher dimensional space. So here is expansion convolution block, and with this expansion residual block we can get a residual connection which is added from the beginning to the end of the module. So the diagram here on the left is the traditional residual block and the right is the described residual block. So the main contribution of efficient DET on YOLO v4 paper is the multi-input weighted residual connections. In the efficient DET paper, it observes that different input features are at different resolutions and it contributes to the output feature unequally. But I already mentioned it in my previous tutorial that we add these features equally instead of weighting input features differently. So that's the difference from efficient DET and YOLO v4. Next, I would like to talk about backup specials for detector, and it includes parts already mentioned. So I already talked about misactivation before in this tutorial, and I covered SPP, SAM and PAN path aggregation blocks in my previous tutorial. So I won't repeat myself, so I will take a brief look in another part, and this is DO and MS, as you can see here. So we already should have heard about non-maximum suppression, and that they filters out boundary boxes that predict the same object and retains one with the highest confidence from following image. So DIO is employed as a factor in non-maximum suppression, and this method takes IOU and the distance between the central points of two bounding boxes when suppressing redundant boxes. So this makes it more robust for the cases with occlusion. That's short, and I will come back to it later. Next is about backs of specials for backbone. So first I will talk about cut mix data augmentation, and best way to explain it is with the following image from cut mix paper. From this image we can see that cutout data augmentation removes a region of an image. This forces the model not to be overconfident on specific features in making classification. However, a portion of the image is filled with useless information, and this is waste. In cut mix, a portion of an image is cut and pasted over another image. The ground truth labels are readjusted proportionally to the area of the patches. For example, 0.6 like a dog and 0.4 like a cat. Conceptually, cut mix has a broader view of what an object might compose of. The cutout area forces the model to learn object classification with different sets of features. This avoids overconfidence. Since that area is replaced with another image, the amount of information in the image and the training efficient will not be impacted significantly also. While reading YOLO 4, I first time faced such a technique that was quite uninteresting to me. Another technique is mosaic data augmentation method that combines 4 training images into one for training instead of 2 in cut mix. So this enhances the detection of objects outside their normal context. In addition, Each mini batch contains a large variant of image, 4x, and therefore reduces the need for large mini batch sizes in estimating the mean and the variance. So that's quite short about that, and you can see actually what is my Mosaic data augmentation from following image. It talks for itself. So next is drop block regularization. So we used to know what is dropout, but in YOLO v4 authors applied fully connected layer drop off to force the model to learn from variety of features instead of being too confident on a few. However, this might not work for convolution layers because neighboring positions are highly correlated. So even some of the pixels are dropped and the spatial information remains detectable. So what is drop block regularization? So it builds on a similar concept that works on convolution layer. So instead of dropping individual pixels, a block of block size by block size of pixels are simply dropped. Next slide is about class label smoothing. In machine learning or deep learning, we usually used to use a lot of regularization techniques such as L1, L2, dropout, and etc. to prevent our model from overfitting. In classification problems, sometimes our model would learn to predict the training examples extremely confidently. This is not good for generalization. So label smoothing adjusts the target upper bound of the prediction to a lower value, say 0.9, and it will use this value instead of 1 in calculating the loss. This concept mitigates overfitting. So label smoothing is a regularization technique for classification problems to prevent the model from predicting the labels too confidently during the training and generalizing poorly. More about label smoothing you can read on my tutorial, text version tutorial. You'll find link to its paper. Next, I will talk about bag of freebies for detector, and first is CIO loss. Generally, a loss function tells us how to adjust a weight to reduce total cost. So in situations where we make wrong predictions, we expect it to give us direction on where to move next. But this is not happening when we use a IOU, when the ground truth box and the prediction do not overlap. So let's consider two predictions. Both do not overlap with the ground truth, and in this situation the IOU loss function cannot tell which prediction is better, even if one might be closer to the ground truth than the other. So in this slide I simply show what is IOU. And here is another slide from the paper which tells us how it's calculated. And here is another slide where it's shown how generalized IOU fixes the problem, finding the loss as following, where we add the C, which is the smallest box covering B and BGT. But this loss function tends to expand the prediction boundary box first until it is overlapped with the ground truth. Then it shrinks to increase IOU. This process requires more iterations than theoretically needed to solve this. So distance IOU loss was introduced. As you can see, this is another function, second function, where B and BGT denote the central point of B and B large and B large GT is the Euclidean distance, and C is the diagonal length of the smallest enclosing box covering the two boxes. And the DIO loss function can be defined as the last function in this slide. And then the finally complete IOU called SciIOU was introduced to increase the overlapping area of the ground truth box and the predicted box, so also minimize the central point distance and maintain the consistency of the box's aspect ratio. So the final definition from the paper is as follows in this slide, and this is the path how it is calculated. And if you need to know more, you can read on the paper, and I'm not going into details this because it's quite hard and for me to understand. Next is cross mini batch normalization. The original batch normalization collects the mean and the variance of the samples within a mini batch to whiten the layer input. However, If the mini batch size is small, these estimations will be noisy. One solution is to estimate them among many mini batches. However, as weights are changing in each iteration, the statistics collected under those weights might become inaccurate under the new weight. This cross-iteration batch normalization estimates those statistics from key previous iterations with the following adjustment is in this slide. Simply talking, CMBN is a modified representation of CBN, which assumes that a batch contains 4 mini batches. Next interesting technique used is self-adversarial training. That's an data augmentation technique. First, it performs a forward pass on training sample. Traditionally, in the backpropagation, we adjust the model weight to improve the detector in detecting objects in specific image, while in self-adversarial training, we change the image such that it can degrade the detector performance the most. In example, it creates an adversarial attack targeted for the current model even though the new image might look visually the same as in the following example. As you can see, for example, if our model detects panda with 58% confidence, we try to find such a noise that it would detect such a different object with a high confidence. For example, this is a gibbon with 99% confidence. Then the model is trained with this new image with the original boundary box and class label. This helps to generalize the model and reduce overfitting. Next, the use is eliminating grid sensitivity technique, and I couldn't find a lot of information about this step, but I know it's known that all YOLO models not do good job of making predictions right around the boundary boxes of anchor box regions. So it's useful to define a box coordinates slightly differently to avoid this problem. So this technique was presented in YOLO v4. We know that the boundary box is computed as follows in this slide, and you can also find this in my previous tutorials. So for the case where bx is equal to cx and bx is equal to cx plus 1, we need tx to have a huge negative and positive value respectively. But we can multiply q with a scaling factor bigger than 1 to make it easier. So here is the source from proposed changes, where they offer to eliminate grid sensitivity by using scale xi parameter from YOLO layer in CFG file, and default scale is 1.0. So this simply tells us how to change 2 lines in code with 4 lines to get this effect. I couldn't find information about this step, but maybe in the future there will be more information on Google. Next is the cosine annealing scheduler. I already using this technique from my YOLO v3 implementation, but okay, let's cover it again. The cosine schedule adjusts the learning rate according to a cosine function. It starts by reducing the large learning rate slowly, then it reduces the learning rate quickly, halfway, and finally ends up with a tiny slope in reducing the learning rate. So in following diagram, it's shown how the learning rate is decided. Also here is learning rate warm-up is also applied, and in this slide you can see this cosine learning rate impact on the map. It might be not very obvious, but this method has more constant progress rather than plateau for a long while before making progress again. So as it's quite everything obvious how it works. So next is optimal hyperparameters. I can't find a lot of information related to this topic, but as I understood, authors offered to select a hyperparameter by using generic algorithms. For example, if we select 100 sets of hyperparameters randomly, then we use them to train 100 models. Later, we select the top 10 performant models for each selected model by map, for example, and then we create a 10 slightly mutated hyperparameters according to its originals. And after that, we retrain the models with the new hyperparameters and select the best models again. As we keep the iterations, we should find the best set of hyperparameters. Alternatively, we can start with the default hyperparameters and then we start the mutation. But anyway, this method takes an enormous amount of time if you're doing this on single GPU, and this is only a project for fun. Next is random training shapes. Also, I can't find a lot of information about this part, but it's known that most single-stage object detectors are trained with a fixed input image shape. To improve generalization, the authors offered to train the model with different image size. So it's called multi-scale training in YOLO. So I couldn't find a lot of information about that, but as I said, maybe in the future there will be more. Where to find it? So now let's move to my practical implementation. Now, as I told, I'll show you how to train your custom YOLO v4 model. And here is my GitHub repository where I have YOLO v3, and on top of it I implemented a YOLO v4. Sorry. And first what you should do is you must get my code, clone my repository, download zip or whatever, and then you should open the file where you cloned it. I have it here. Then you go here and download the model weights you want to test or train on with transfer learning. If you don't want to use transfer learning, or it doesn't matter for you. So, but first I recommend you to train on my MNIST dataset, where I show you how to do that. So we simply open my repository terminal and we copy commands from my GitHub repository simply. So first I extract my MNIST dataset and that's it. And I make training files. Then, as you can see, we must do a Python train py, but it's by default configured for YOLO v3. So you should open my folder and go to YOLO v3, open config. I already changed it, but by default this will be 3. Change it to 4. Then if you are not using tiny, leave it here as false. Then train class should be MNIST name, train annotation and path is MNIST train txt, and here is also MNIST test txt in test annotation path. So next we use our transfer learning as true and input size as 460, batch size of 8, but leave it as it is. So this is the main things you should change. So I can close this because I have configured it to YOLO v4. Then I go to my train py file. I'll use my first GPU because I'm recording on my 0 GPU. And at the end here of script, you might see here is a line for to measure a map of trained custom model. Okay, I'll set this to do on every epoch. So it's not recommended, but I'll do this now to show how it works and how it trains, and that's it. And why I don't recommend to do this, because it requires much more resources and more time to measure map on each episode. So I'll only show this for you here. So I open a terminal and I simply write a python train.py, and it should begin training in a moment. It transfers the layers from YOLO v4. So that's it. As you can see, it started, and let's wait till it finish first epoch to see the map. As you can see, it gave me map of 0, because actually it was only a first epoch, and we should start seeing the results in somewhere around third epoch or fourth. So let's wait for it. So I think this is enough. We achieved a map of 82, and of course it would be best to train 100 epochs, but I don't need it right now. So let's close it. And of course I think you would like to see the results. Yeah. There is a TectMNSPy script. Let's open it, and this way you would test your custom trained model, and there should be 3 files in your checkpoints folder, and as following: one is custom index, one a bigger file, and one for checkpoints. So that's it. And where's my script? Here it is. And of course then you can close it. I just show you what is inside. Detect MNSPy it is. So I write on Python detect mns.py, and right now the detection will be made on CPU, not GPU, so it will be a little slower, and as you can see, it detects what it needs to detect actually, but it's not that accurate because, as you saw, I trained it only for 8 epochs. So let's check another one example, another image, what it will show me. Let's wait a little. Here's only 7 and 3, but actually, as you can see, it works, and it's trained on YOLO v4 actually. One more, okay? What's this? Oh, it went to my another window. So as you can see, everything is just fine. So in summary, the YOLO v4 authors offered a state-of-the-art detector which is faster in terms of frames per second and more accurate on COCO AP and all available alternative detectors. So it's better than all available alternative detectors compared average precision with frames per second. And also, what is nice that YOLO v4 can be trained and used on a convolutional GPU with 8 to 60 gigabytes VRAM, which are broadly available. In the previous version v3, it was very difficult to train model on such GPUs, and you had to do some kind of workarounds. But right now, it's a little better, but it doesn't matter for you. And I must say a big well done to the authors for having verified a large number of features and selected for use, such as them for improving the accuracy of both the classifier and the detector. And their offered features can be used as best practice for future studies and developments. So, and as you can see, I implemented my YOLO v4 architecture on top of my YOLO v3 implementation, and you can run this with TensorFlow too. But sadly, I didn't have time to implement all these backup freebies I mentioned to improve the training process. Maybe later I'll find time to do that, but now I'll leave it as it is. So you can clone my GitHub repository as I shown to you. and tested out how to train it written in the README file. So it's quite simple and similar to YOLO v3, and that's it. And right now, in the next part, I'm interested to test the results with TensorRT, how to convert model to it, and I hope to receive a quite high frames per second with YOLO v4 and YOLO v3. And what my goal is, if I'll achieve a good results, I'll test this on my aimbot. If you remember, I did a Counter-Strike aimbot, and if I'll get, for example, 50-40 frames per second with detection, yeah, that's a chance for me to train again Counter-Strike enemies detection and to see if it works better with a faster detection. So thank you all for watching, and hope to see you soon in the next tutorial. Thank you all for watching. Subscribe me, like my videos, comment if you have questions or whatever, and see you next time. Goodbye.